Hi, this is Dr. Epling. This is Evidence-Based Medicine. This presentation is about working the 2x2 table, understanding the diagnostic testing statistics that we have available to us. This is a skill you'll have to practice. It comes with going over it, and hopefully this video can help a little bit. After this, I want you to be able to define, calculate, and solve problems with these concepts, these statistics: prevalence, sensitivity and specificity, predictive values, and likelihood ratios. And we're going to talk very simply about Bayesian reasoning, this idea that a test merely changes the probability of the disease from a before the test to after the test. And so we'll talk about this at the end of the video. So the 2x2 table, here's the essential components of the 2x2 table. You have the disease in these columns. This is defined by the reference standard, the ideal diagnostic test for the condition that confirms the disease. This is the test of interest down here. In the colon cancer case, we're going to talk about fecal occult blood testing as the test of interest and colonoscopy with biopsy as the reference standard. Remember that in the ideal diagnostic test study, you have patients that get both the test and the reference standard independently. In other words, the application of the reference standard doesn't depend on the test result. Everybody gets both the test and the reference standard. That allows you to fill in all of these different squares here. Okay. So sensitivity, specificity, the calculations are here. Using the letters from this table, you see A over A plus C for sensitivity, D over B plus D. Watch that D. It's D over B plus D for specificity. Note here that in the English version of these, we talk about the proportion of the people with the disease who are test positive and the proportion of people without the disease. In other words, what are we starting from? We're starting from knowing whether people have the disease and seeing if they test positive. We'll come back to that when we talk about predictive values. This is not really the way clinicians think. Clinicians get tests and have to figure out if those tests means that people have the disease or not. Prevalence here is that disease positive column, A plus C, will flip back, A plus C, and over all four numbers. So the prevalence is merely that disease positive column over the total population. Okay. The other word for this is pre-test probability. In other words, we use these terms in kind of interchangeably. If somebody just walks into your office, the prevalence of any given disease can kind of be applied to the person that walks in your office until you know more about them. So if for somebody walks in just off the street, they have a baseline risk of colon cancer of roughly 6%. But if I know that they have had rectal bleeding or there's a big family history of colon cancer or something like that, each additional piece of information might increase their pretest probability a little bit. And it's this pretest probability that we start with in Bayesian reasoning. So here's the table for sensitivity here. Here's my clever animation. So for sensitivity, you have the true positives in this cell over a combination of the true positives and the false negatives, or A over A plus C. And this gives you the sensitivity. For specificity, it's kind of the opposite. You have D, the true negatives, over all the disease negatives, B plus D. So you can see how that goes. Now, positive predictive value, on the other hand, looks at this slightly a different way. It takes, if you recall the 2x2 table, which I'll kind of briefly put up over here, A, B, C, and D in my really nice handwriting. A over A plus B goes this way in the table, doesn't it? So it's taking what we know about from the test and figuring out whether or not somebody has the disease on this side, okay? So it's the proportion of patients with positive tests that then go on to actually have the disease. Negative predictive value, portion of people with negative tests. So negative test negative. Oops, that's negative. Test negative over here over all test negatives. So true negative over all test negatives. So here we have an illustration of positive predictive value, the true positives over all test positives, okay, and for specificity, or for negative predictive value rather, we have the true negatives over all test negatives. Okay, should be fairly straightforward. Go over that again when you get a chance. So just to re-emphasize my really entirely too busy diagram here is that I want you to realize predictive values go this way in the table, the way clinicians think about things. Do you have a test result, and does that mean that the patient has the disease? Compare that to sensitivity and specificity, which are more like what a pathologist would use if they're deciding on buying a certain test for their laboratory. They want to know that the test is accurate and the test can be applied to different populations and such. And that you need sensitivity and specificity for. For clinicians, we need a different way to think about this. All right. So inevitably on your standardized exams, whether it be specialty boards or step exams or whatever, you'll run across a variant of this problem. They give you a certain amount, they're testing some test in some sort of population for some disease, okay? And I've just labeled those with letters so that we don't get caught up in the actual medicine of it, heaven forbid. But what they'll give you is a certain minimum amount of data that you need to know about this particular test. And it's usually some result of some study. So here they've given you the positive predictive value, the sensitivity, and the prevalence. You have to have some idea of the prevalence to make this whole situation work here, but they can vary these other statistics up here and give you other parts of them. They may give you more data than you need, but you'll be able to figure that out. The key to this is it's not quite enough to just go calculating almost directly. You have to do a little bit of work to understand, using some of the principles that we talked about, that sensitivity and specificity don't change, in order to figure out this example. So the principles, one, sensitivity and specificity don't change. So one principle is that we have to somehow develop the sensitivity and specificity for this particular diagnostic test, or we can't move any further. But what it's asking you to do, what it will ultimately ask you to do, is how does this test work at a different prevalence level? And we'll see that in a second. But let's start with the beginning here. So the best recommendation I have is to use a pretend sample size of 1,000. Why? Just because it gives you enough significant figures to be able to do the calculations with. So the whole population, A plus B plus C plus D, is 1,000. Okay? Now, what we know, if we're given the prevalence values, and we generally need to be, is that that's a certain amount of the population. In this case, it's 10%. 10% of the overall population is 100, right? Remember, when you're doing these conversions, I'm writing them as percentages, but remember to convert them into decimals. For instance, this is now 0.85, okay? So remember to actually convert them to decimals before you start multiplying. So anyway, back to this. So the prevalence of the disease, all the disease positives, A plus C, equals 10% of 1,000, or 100. So this whole column is 100. This whole column is 1,000 minus 100, which is 900. Okay, pretty straightforward. Okay, now you're going to use this sensitivity to be able to calculate this. So if we know that sensitivity is A over, sorry about that, A plus C, and so that means you have a sensitivity of 0.85 equals A over A plus C. And we know A plus C is 100. So A over 100 equals 0.85. A then equals 85, right? Just moving this over. So 85 people belong in box A. Subtraction gives you 100 minus 85, gives you 15 in box C. Okay. So that's how you fill in those dots, and then you do the same thing on the other side. Sorry, you do a similar calculation. This time you use the positive predictive value calculation. So you can't go straight to the sensitivity or to the specificity calculation because we haven't given you specificity in this. That would be down here. Instead, we have given you positive predictive value. You know that the A part of the positive predictive value is here. So positive predictive value equals A over A plus B. So positive predictive value is 0.65, that's given to you in the problem, equals A 0.85, or sorry, 85, 85 over A 85 plus B. And then you basically solve for B. And solving for B gives you 45. Okay, so that's how you fill in cell number B there. Now that you have that, and you have the overall population, you can begin to calculate the specificity. And that's what you want to get to. You want to get to sensitivity and specificity. Okay, so now we need to calculate what happens in D here. And so we have the total 900 minus 45 is 855. And so we've been able to solve for all four boxes, A, B, C, and D. And now we can calculate the specificity, which is D over B plus D, which is 855 over 900. Okay, that gives you a specificity of 95%. That's good. So now we have sensitivity and specificity. We can do the next part of this. So usually in the question, they'll ask you, okay, so for population B, we just calculated population A, the prevalence is now 30%, and they'll ask you, well, how does the test work there? Hopefully what you've already internalized is that predictive values can't be taken to different pretest probabilities or different prevalences. We need to calculate back to sensitivity and specificity first, and then recalculate the predictive values based on the new prevalence. Okay, sensitivity and specificity are properties of the test and do not change, whereas predictive values do change with that. And we'll reinforce that a little bit later. Okay, so you have a prevalence of 30. You start with your made-up population of 1,000. 30% of 1,000 is 300, so that's the prevalence with the disease. And then the proportion of people without the disease is 700. Should be pretty straightforward. And now you just calculate to fill in these columns using the sensitivity and the specificity. Just to go over the sensitivity calculation, it's the sensitivity, 0.85, equals A plus C, so you put that in the denominator, 300 over under A, so A over A plus C. So you multiply 0.85 times 300 and you get the value for A, and then you subtract that from the total and you get the value for B. And here it is. So 85% of 300 is 255. 300, the prevalence minus 255 is 45, and same deal over here. The specificity is 95%, so D over 95% over B plus D, 700, is 665, and then you subtract it and you get 35 for the B column. Okay, pretty straightforward. Now hopefully you can see what we're going to do. We're going to calculate predictive values using this data. Should be pretty straightforward. Just for grins, we'll do the negative predictive value. So negative predictive value is D over C plus D. That should be a C. Okay, which is 665 over C plus D is 665 plus 45. 65 plus 45. And there it is, 94%. Positive predictive value is 88%. Okay, so now we've gotten to the new predictive values in this higher prevalence population. And that's usually they'll give you, one of these will usually be the answer for this. Sensitivity and specificity don't change. Positive and negative predictive value do change. And here is that demonstration. So at the prevalence that we had of 10%, positive predictive value was 65, negative predictive value 98. In the case of a rising prevalence, the positive predictive value increases, the negative predictive value decreases. And that's true for all predictive values. As the prevalence increases, as your baseline more likely to have the disease, your positive predictive value will increase. Just the test will be more likely to give you a positive result. Prevalence increases, the test will be less likely to give you a negative result. Conversely, when the prevalence decreases, your negative predictive value will increase. The less likely you are to have the disease, the less likely the test will tell you that you have the disease. So the likelihood of the condition before you test influences the interpretation of the test results. And you might take some offense at that. You might say, well, that's not a very useful test. Well, that's part of the problem with these statistics and why likelihood ratios can help us somewhat with that. But at baseline, this is true no matter what test we use, no matter what test statistics we use. It's always going to be influenced by the likelihood of the condition prior to the test. So if we calculate likelihood ratios, these are the equations. Likelihood ratio for positive test is sensitivity over 1 minus specificity. So what do we have here? We have the likelihood ratio of items that don't change with prevalence. So we can use these likelihood ratios at different prevalences, and we'll show you how that works in a second. So you calculate them using sensitivities. The bigger equation for this likelihood ratio for positive test is sensitivity, which is A over A plus C, over 1 minus specificity. If specificity is D over B plus D, then 1 minus specificity is B over B plus D, right? Work that out in your head. So B over B plus D. Okay, so that's the calculation for a likelihood ratio for a positive test. Similarly, for a negative test, you have 1 minus sensitivity, which is C over A plus C, all over D, specificity, over B plus D. Okay, so here it is for likelihood ratio for a negative test. You see the calculations here, and you end up with these numbers. Big whoop. What do those mean? Well, let's talk about it. It's kind of like ruling in and ruling out disease. The unfortunate thing, likelihood ratios were developed odds in general. So the odds of a disease, if you have a 10% chance of something, then that's a 1 in 10 chance, but it's 1 to 9 odds. It's hard for us to think in terms of odds. It's not a very intuitive concept. So instead of, but this is how you would have to do it. So 1 to 9 odds, you multiply it by the likelihood ratio, and you get post-test odds, whatever those are. I'm supposed to say post. The problem is we don't think in terms of that, and there is a whole calculation for taking odds, converting it to probabilities, or sorry, taking probabilities, converting it to odds, multiplying by a likelihood ratio, getting post-test odds, and converting it back to probabilities. That's too much math, so we use something called a nomogram. A nomogram is basically like a slide rule. It helps us take a pretest probability, gives us ranges for a likelihood ratio, and gives us a post-test probability. So if we say the pretest probability is 20%, and the likelihood ratio is somewhere around 3.7 here, so 20% here, 3.7, we draw a line between those, and we hit a post-test probability. So this is just a way of doing that fancy math without actually doing the calculations. We get a post-test probability around 43, 45, somewhere around there. Okay, so that's what this Fagan nomogram, F-A-G-A-N, nomogram is for. Now, if you don't happen to have a Fagan nomogram every time you're reading a diagnostic test article, you could use this sort of go-by for figuring out what likelihood ratios mean. And what it basically divides the world, so likelihood ratios, these are likelihood ratios for a positive test, and these are likelihood ratios for a negative test. So all this means is if a likelihood ratio greater than 10, it's strong evidence to rule in a disease. 5 to 10, moderate evidence. 1 to 2 is pretty weak evidence or indeterminate. This particular diagram says that anything that's surrounding 1, which for a ratio, since these are ratios, 1 is kind of you can think of as a line of no effect. In other words, it doesn't really change the probability that much. For likelihood ratios for negative tests, 0.2 to 0.5 is okay, is weak. 0.1 to 0.2 is pretty moderate evidence, and less than 0.1 is strong evidence. Look at it like this. 10 inverted is 1. 5 inverted is 0.2. 10 inverted is 0.1. These are relationships to each other, and you can look at it that way. caution you, there is still an influence of low prevalence. If there's extremely low prevalence, even a high likelihood ratio test, either a really good likelihood ratio negative or a very high likelihood ratio positive, can still be kind of misleading if you really have an extreme of prevalence, either a real high prevalence or real low prevalence. So some examples, say somebody's at real high risk of a disease and they have a pretty decent likelihood ratio. What is that, 7.5, something like that? You go from a 90% probability they have the disease to a 98.5% probability of the disease. So the question is, given such a high pretest probability, why bother doing the test if it's only going to make you that much more sure that they have the disease? Okay, so it's not that it's misleading in this case because it goes the right direction, but it didn't do you much good at convincing you that they had the disease because you were already pretty sure. Similarly, at a real low prevalence, 2% risk, with a decent likelihood ratio, you've increased, so a likelihood ratio for a positive test, LR positive, of 5, which we said was at least moderate evidence, your suspicion of disease only goes up to about 8%. So you've gone from 2 to 8. So in somebody that has really low pretest probability, you're not making yourself much more certain at all that they have the disease here. So that's what I'm talking about, that sensitivity or the reliance on pretest probability to tell you how well your test can work. Similarly, for negative likelihood ratios, or likelihood ratio for a negative test, starting at a very low prevalence to begin with, and you get a decent, though not great, likelihood ratio for a negative test, it doesn't decrease the likelihood that much. It goes from 2% to 0.5%. Are you really that much less sure about the disease at that point? If somebody has a real high pretest probability and you do a fairly good test, 0.1, you've only get down to 50% probability. So that's kind of a coin flip, right? You've gone from pretty sure the patient has a disease to, well, I didn't completely rule it out, and the patient has a 50-50 chance of still having the disease. It doesn't do that much for your decision making. So you would need an extraordinarily good test, to get down to a 1% pretest probability, right? Because the line would be across this way. So you need a whopper of a likelihood ratio for a negative test. Hopefully we've been able to illustrate some calculations, some use of the Fagan nomogram, and how that lets you understand the impact of pretest probability and likelihood ratios on how you're diagnosing disease. So hopefully enjoy that, and I'll see you next time.